Yes. May I use?
Well, I think that just as a continuation of the comment that we just made, I don't think there is, or at least this is my impression, we are not so much in disagreement on the challenges that we have to build a fusion reactor. The disagreement or the discussion, if you want, is more on the roadmap for solving this issue. So it's not so much, I think all the people agree on the key problems, but the way in which we can solve these problems is the discussion that we have. I think that in this preliminary talk, what I will say is to insist again on some of the ideas that has been already presented or put on the table several times. And I try to not to think too much on the near term, not to think too much on the specific plasma machine we are talking about, or even the inertial machine we are talking about, but I wanted to make a comment on the long term. I want to emphasize, and I think this is very important, we must have this in mind, that the feasibility of fusion as an energy source, even I'm not talking about commercialization. I mean, if we want to be able to compete with solar photovoltaics, or we want to compete with fission, nuclear fission, we need to control or progress in these three key parameters of a fusion reactor. First is the tritium self-sufficiency. This has been mentioned several times. I'm not sure if it is fully clear what that means. The fuel for a fusion reaction is deuterium and tritium. Tritium is not available in nature, so we need to produce it by ourselves in a fusion reactor in such a way that the tritium that we burn in the fusion reaction, we reproduce in some way and we recycle. This is a key parameter that is mandatory, but it's not the only one that is very important. If we dream that fusion can become a significant player in the electrical system at some moment in the future, that means that we need to build a few hundred reactors. I mean, 10% of the electricity market means around 1,000 reactors. And that means that if we want to implement fusion fast in the system, we cannot rely on the tritium that will be produced by the previous generation of reactors. We need to produce tritium in some other place. And my impression is that we are not thinking too much on this. We need to produce tritium outside of a fusion reactor to be able to allow for a fast implementation of fusion in case we are able to demonstrate that fusion is feasible. This is not an obvious thing to develop this point. The second thing that will be very important to demonstrate the feasibility of a fusion reactor is the availability. I mean, it is not the same if the reactor is working 1% of the time or if it is working 99% of the time. The availability of the reactor is a key parameter that must be improve a lot or must be developed. Of course, the first one does not need to be high availability. This is obvious. But in the long term, the availability of the reactors must be high enough to be able to be cost efficient. And the availability is a complex function, of course, of the design. I mean, one way to improve availability is with redundancy in some of the systems. It is also a function of the lifetime of the materials. If I need to replace the materials each week, the availability will be very low. If the materials are able to survive 20 years, the availability will be higher. And also on the maintenance strategy, and especially on remote handling, on remote maintenance strategy. If I am able to replace the broken components in one day, it will be much faster than if we need 6 months to make a replacement operation. So this aspect is something that is very important. And finally, the third parameter that to me, we do not talk too much about it, but is also essential, is the efficiency of the reactor. I mean, the ratio between fusion power, the power that is generated in the fusion reactions, and the electrical output that we get. And of course, this again depends a lot on the different parameters, but there is one key parameter that is very important to improve the efficiency of a reactor, that is the working temperature of the cooling fluid. So if we want to have a relatively high efficiency, we must work at high or highest temperatures. Today, the designs that we have work at 300, 400, 500 degrees centigrade, and this is very low efficiency. We need to be able to go to much higher temperatures, and it's not obvious. We work at these temperatures because we don't have alternative at this moment, but we need to think that these things must be solved. So these three relevant parameters can be, of course, translated to a number of significant technology issues that needs to be solved, and I think most of them has been already mentioned. Tritium breeding and extraction technologies, the heat and particles exhaust from the plasma, materials and material systems. When I mention here material systems, is what I try to say is that it is not only, the important thing is not only the bulk materials properties. I mean, I can take a piece of steel and I can study the properties of this steel. But the important thing is that this steel will be welded with another material. It will have a coating on top of it. It will be working close to a liquid metal to it. This thing will not work exactly the same that the individual materials properties. I need to know also how the materials will behave in the more or less complex environment in which it will be used. The other technology issue that I mentioned is maintenance by remote handling, high temperature operation, and of course, we have not talked too much about this morning, safety and environmental impact. This is also a key thing that Carlos mentioned this morning, but it can have a very significant impact on the design of any machine. I have not designed a fusion reactor, never, but I am working in the IFMI project that has been mentioned before, and I can tell you that the complexity of the accelerator increased by a factor of 2 or 3 just due to safety considerations. Safety aspects make things much more complicated. All these technology issues that I mentioned has been mentioned several times here, but it appears also in a recent document by IAEA that is fusion key elements that has been published, I think, late last year. So, in principle, the idea here was to talk a little bit about materials. So, I recycle a very old slide that was used many years ago, in which I tried to make a sketch of the different type of materials that we are talking about. There are a number of components in which the materials properties are key. It has been mentioned several times, the breathing blanket, the divertor, but also all the systems that we need to use to control what is happening in the plasma, all the things related with diagnostics and also some other systems. This, of course, the requirements that I will put on the materials will depend on the design that I have for these components. If I change the design of the component, the requirements to the materials will change. But, making a high-level summary, you can see there the number of topics that must be taken into account when we talk about materials. Not all the requirements goes to all the materials, but in general, most of them are relevant. Of course, one very important parameter is radiation resistance. There will be a lot of neutrons, and we must be able to demonstrate that the materials work up to as high as possible level of neutrons. But as I already mentioned, there are other properties, I mean, corrosion, compatibility with coolants, other physical properties, reproducibility in the fabrication of the materials, and some other things that are really critical if we want to be sure that these materials can be used in a fusion reactor. And then I also put here a list of materials we are talking about. Usually, when we talk about materials, most of the people think on structural materials, that the ones that we have today is rough steel, low activation steels, but there are others that are being discussed, like silicon carbide composites, tungsten alloys, the size of the letter is more or less proportional to the degree of knowledge that we have for this material. So if we want to build a fusion reactor today, in my opinion, the only alternative is rough steel. Maybe in 20 or 30 years from now, there are other materials that can be used. This is for structural properties. Of course, tungsten can be used also for heat extraction, for first wall material, and in this case, the knowledge that we have for the behavioral material is it's much higher. There are also what we call functional materials that are, functional means that we are not interested on the mechanical properties, but we are interested in the physical properties of this material, in different type of physical properties. And that means that they are much more sensitive to radiation than in the case of structural materials. So you can see there that we are talking about beryllium and beryllium alloys and some lithium ceramics. And there are other family of functional materials that are diagnostics, that are for diagnostics in which the key materials we are talking about are oxides or diamond. And I think I already talked too much, so that's
no,
all
you
from my
haven't talked
side.
too much.
That's
There's
starting
lots more
point.
to learn, but we're going to learn it, and I'm going to stop you now.
Yes.
I'm grateful to you for keeping
So
the time.
thank you very much.
Thank you, Ángel. Thank you, thank you.